Hi guys, this is Mr. Adams from Midway High School, and today we're looking at periodic trends. I know I did a video on this already, but I'm doing a demo to emphasize the trends down a group. And before I do that demo, I'm going to do some recapping, okay? So our test is coming up soon, right? And you have to know what periodic law means. Essentially, that the periodic table is ordered through the atomic number of protons, right? You have to know what a group versus a period is. A group is the vertical column, okay? It's also called a family, all right? Same number of valence electrons in a family, similar chemical reactivity, and the period is a horizontal row, okay? All the guys having the same number of principal energy levels. You got to know what valence electrons mean. Valence electrons are the outer electrons in the outermost shell, okay? You have to know what shells or principal energy levels are, because those are important also. So there's the energy levels that the valence electrons are in when we have our electron configurations. You have to know what nuclear charge is, okay? Remember, there's protons and neutrons in the nucleus, and the nuclear charge comes from the protons. So if you have 5 protons, your nuclear charge will be +5, and so on. Now, Coulombic attraction, right, or just attraction, governs this whole topic of trends, people. So once again, it's affected by magnitude and distance, okay? So the thing is, folks, we specifically talk about valence electrons and protons in the nucleus, okay? Those the attraction between those two guys we focus on. So if we look over here, guys, once again, if you have, say, one proton attracting one electron, right? And you have a number of protons attracting a number of valence electrons, this second situation right here would have a stronger attraction. So that's what I mean by magnitude. The more positive, the more negative you have attracting each other, the stronger the attraction, as opposed to just a lower number of positive and negative, okay? And also, folks, distance. We have one proton here, we have one proton way over there, right? Versus one proton here and one proton there. Now, one electron there. Now, this situation, right, the second one right here would have a stronger attraction. Why? Because the distance is less. Okay, so once again, one proton, one electron, one proton, one electron. But this one has a stronger attraction because why? Because the distance is less, so the attraction is stronger. This situation right here, more charge, more positive, more negative, a stronger attraction because of the magnitude, higher magnitude. Alrighty, let's look at trends across a period, okay? Now, as we go across a period, right, we're in period, see that funny little 3 right there? We're going across period 3. Notice there's all of them have 3 energy levels that I drew there, okay? No problem. And you also notice, right, the number of protons, 11, 12, 13, 14, 15, are increasing. Now, what's happening, folks, as we go from left to right? The protons are increasing. The valence electrons are also increasing, okay? So our charge is increasing, right? But the principal energy levels, if you notice, 3, 3, 3 all across, they're staying the same, okay? So what's going to happen, people, as we go from left to right across a period? Remember, horizontal row is a period, right? Okay, the attraction will increase, okay? And that's very important. So how is it going to affect these guys right here, i.e. ionization energy? Now, before we start understanding trends, people, you have to understand what attraction does. Then you have to know your definitions. So ionization energy, right, is the energy needed to remove or steal a valence electron, okay? So you want to come along, you want to take off a valence electron off of one of these guys. It's the amount of energy you need to pull it off, basically, okay? All right, electronegativity now is the attraction an atom has for electrons in a bond. Now, if these guys were bonding with something else, right, and you would think of it as a tug of war, the ability for that atom to pull electrons towards itself is basically called electronegativity. Now, we simplify the definition of atomic radius. Okay, when you guys go to college, there's a bit more emphasis on it. But basically, for our purposes, it's going to be the size of the atom, okay, atomic radius, all right? And metallic character is going to be the easiest with which you lose valence electrons, okay? You're behaving more like a metal, the more more easily you lose valence electrons, okay? So what's going to happen, folks? we establish, right, that attraction is increasing as we go from left to right. This right here, we have 11 protons and 1 valence electron, versus over here, we got 17 protons in chlorine attracting 7 valence electrons. Higher magnitude of charge, okay, increase attraction. So when you come along now and try to take off electron off of chlorine and take off one valence electron off of sodium, the chlorine, okay, is gonna take a lot more effort for you to pull it off. So when the going from left to right, the ionization energy will increase. It takes more energy to remove, okay, electrons off of the guys on the right side, these non-metal guys, as opposed to these metals on the left, okay? In terms of electronegativity, right, it will be considered that you're going to look at the attraction again. We agree the attraction is going to increase from left to right, okay? So the ability for the atoms to pull electrons toward itself, once again, the guys on the right side are going to win, are going to be higher in electronegativity. Okay, so if you have 17 protons versus 11 protons, okay, 1 electron versus what? It's only 7 right there. Okay, you're going to have a better and stronger ability to draw electrons toward yourself. Okay, so the guys on the right side, from left to right, guys on the right side have higher electronegativities. So the electronegativity increases as you go left to right. Okay, moving on. Atomic radius. Now here's the deal. We just go with attraction, people. The attraction is increasing left to right. More protons, more electrons, more valence electrons, okay? The valence shell gets pulled closer and closer and closer to the nucleus, okay, as the nuclear charge increases. So what's going to happen to the size of the atom? It will actually start to get smaller and smaller as you go left to right. So the atomic radius decreases as you go left to right, okay? And metallic character, okay? What's going to happen as you go left to right? It's going to be harder and harder for you to lose electrons. How come? Attraction is stronger, okay? These guys on the right side are holding on to their electrons much more strongly than these guys over here. So once again, ionization energy goes up, electronegativity goes up, the atomic radius, size of the atom gets smaller, and in terms of metallic character, okay, that also decreases. All right, so I'm going to do the demo in a second. All right, guys, we're going to look at the trend down a group right now, and we have 3 different alkali metals. We have lithium, okay, we have here sodium, okay, and we have our good friend from the last video, potassium, okay? So what we're going to do, we're going to take bits and pieces of these guys, we're going to put it in these small containers of water right there, and we're going to look at how rapidly and how vigorously they react with the water, okay? Now remember, these guys are alkali metals, so we're expecting that when we put our red litmus in, we'll get a color change, right? So we'll do that in a second. All right, guys, see that right here? I got a piece of lithium that I cut in half right there. I don't know if you can see the outer part being kind of dull and the inner part being kind of shiny, right? Because lithium, okay, reacts with the things around it, and it got corroded on the outside, right? But in the inside, it still has luster, all right? We talked about that recently, yes? All right, so I'm going to put that inside the water right here. I'm going to see what happens. Okay, see that? That's pretty cool, right? Okay. Alrighty. See that? Nice and blue. All right, guys. Here, I have sodium, which I cut up in a couple of pieces. Okay, so we're going to see what happens to this. Okay, see that? Okay, much more rapid. Then the lithium, see some fire right there. Okay. And test it again. Bam. Basic solution produced. Alkali metal. Because remember, alkali means basic, right? Last but not least is our good friend potassium. We're going to drop it in and we're going to see what happens. So let's go. Wow. Beautiful. Okay. That was pretty fast. Okay. And rapid in terms of the way it generated the fire. Let's see what happens when you poke in the flame. Okay, nice blue color once again. Alkali metal. Bam. Okay, so let's wrap it up. Trends down a group, right? From the demonstration, we did lithium, sodium, and potassium, right? And we saw that as we went down the group, the reactions got more rapid, more vigorous, right? We saw rapidly the potassium reaction take place and was over, and it generated fire much more quickly, right? Now, the thing is, we want to look at the experiments. We just don't want to say, wow, and that's it. We want to understand the chemistry behind it, right? So as we're going down the group, protons increase, yes? Okay, because you're going from what? 3 to 11 to 19 and so on, right? Okay, the number of electrons increase, okay? The valence electrons stay the same within the group, but the number of electrons overall are increasing. So in terms of protons and electrons, we are expecting what? We're expecting attraction to increase, right? But we have to take something else into consideration that we didn't have to when we're going to cross a period. The number of principal energy levels are also increasing, folks. So look at over here. Here we have 2 energy levels, 2-1, okay? All right, here we have for sodium 3 energy levels, 281. For potassium, we have 2881. Now look what's happening to the valence electron in relation to the nucleus as we go down more and more the group, right? The more we go down the groups, the further the valence electron is away from the nucleus, from the nuclear charge. And what do we agree, folks? The further you're away, distance, okay, increased distance weakens attraction, okay? And there's another factor that we talked about in class. We talked about the fact that there's more and more principal energy levels between the valence electrons and the nuclear charge, right? So lithium, okay, this valence electron right here has only one shell blocking or shielding the attraction between the valence shell and the nucleus, right? Now over here, cesium has all of these shells, okay, blocking the attraction of this outer one valence electron to the nucleus. So even though cesium, right, has a whole bunch more protons, he has all of these other valence, these shells blocking the attraction to this valence electron, okay? Because remember, electrons are in these shells, right? So you have these guys blocking attraction, plus you have increased distance from the nucleus that makes cesium attraction very weak compared to something like lithium, all right, within the same group. So as you go down the group, your ability, the energy you need to take off this electron, okay, the electrons will come off much more easily. So you don't need that much energy to remove an electron from cesium as you would for something like sodium or lithium. So down the group, ionization energy decreases. Why? Because attraction is weakened. As you go down the group, attraction gets weaker. The ability to draw or attract electrons towards yourself gets weaker also. So electronegativity decreases. So once again, ionization energy decreases down a group. Electronegativity decreases down a group. What happens to atomic radius? Well, the configurations tell you what's happening, right? The more principal energy levels that are added, the larger the atom gets. Bam, done. Okay. And in terms of metallic character, right, the ease with which you lose electrons, okay, to behave like a metal, more and more like a metal, Remember, the attraction is decreasing down here from top to bottom because of shielding, because of increased distance. So this electron right here comes off very easily, is lost very easily. Why? Because the attraction is weak, okay, compared to the guys that are up here. So the metallic character decreases. So once again, ionization energy, metallic character increases. So once again, folks, let's go slowly. Ionization energy decreases, okay, because of weak attraction. Electronegativity decreases. The atomic radius, right, gets larger, okay, and metallic character, okay, increases. It's easier for this guy to lose electrons and behave more and more like a metal, which it is. Okay, guys, as always, hard work plus sacrifice equals success. Study, 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 do well.